Okay, welcome everybody. So today we are very happy to have Zahraee from McGill. She's going to tell us about low spin analyticity in the 3D Ising model. Okay, go ahead.
Thank you. First, I want to thank the organizers for inviting me. It's a great pleasure. Today, I will talk about low spin analyticity in 3D Ising CFT. It's based on a paper which came out in July in collaboration with Simone Karen-Hood and Jan Gobet. The broad motivation of this work is to understand and organize the spectrum of the 3D Ising CFT by using analytic methods. Our approach is to ask questions about real-time dynamics of the 2+1D Ising CFT. One obvious advantage of this is that real-time dynamics offers more kinematic limits to explore as opposed to just the Euclidean OPE. And the bonus we get is that lots of ideas and techniques can be borrowed from the study of the asymmetrics to understand the spectrum. For example, Forsyth-Gribov formula and analyticity in a spin, and the Regge limit and high energy scattering. These are all examples of ideas which can be borrowed. In this work, we ask two questions in this direction. So the first question has the following setup. Consider a scattering of two pairs of highly boosted lumps of positive spin. Here, lump 1 and 4 are time-like separated from each other, and lumps 2 and 3 are also time-like. All other separation are space-like. So our question is as follows. Is high energy scattering, is the scattering that we just described in 3D Ising CFT transparent or opaque? This setup describes the scattering in the Regge limit. So that's where we will look for to answer our question. The second question has the following setup. It has been previously shown that the CFT data is analytic for j bigger than 1. This organizes CFT operators into different families, which can be parameterized as follows in terms of spin and twist, where twist is given as conformal dimension minus spin. Here, gamma is the anomalous dimension, which at large j approaches 0. These families are naturally plotted in j delta plane, and they define the Regge trajectories of the CFT. Within the epsilon expansion, this analyticity has been extended, and it was shown that the epsilon belongs to the analytically continued branch of the leading Regge trajectory. So our question is as follows. Does this extended analyticity continue to exist beyond epsilon expansion in 3D Ising as well or not? We can ask the same question about sigma operator. Is that the analyticity of the odd trajectory extendable or not? So that it would include the spin 0 operator, either sigma or shadow. So the first question is illustrated in the plot here. The red dot, the question is basically whether the red dot is epsilon or not. Yeah, for related analysis in O2 model, see the paper which came out in July of this year as well by Leo Meltzer, Poland, and Simmons-Duffin. Okay, so the outline of the talk is as follows. We built some background to be able to answer the questions, and then we move to the 3D Ising CFT looking for the answers. First, let's study the Regge limit. We study the correlation function, the building block, the object we use the most is the correlation function of 4 scalar primary operators, which is given as a function of 2 cross ratios. We study this correlator in the Regge kinematic. We begin by all operators space-like separated from each other, and then we apply a large boost operator 1 and 2 to go to the Regge limit. This is most nicely described in rho and rho bar variable, where here, after the large boost, rho bar goes to infinity and rho goes to 0. And eta here is our boost parameter. In terms of cross ratio, this is equivalent to analytically continuing the correlator from z bar equal z star around this branch cut, around this branch point at z bar equal 1 to build the analytically continued correlator. From conformal Regge theory, we know that the limit, the large boost limit of the correlator that we just described is exponentially dependent on the boost factor, and with the prefactor j star minus 1 here. J star is the intercept of the leading Regge trajectory, which is where the Regge trajectory intersect the j axis. When j star is less than 1, g approaches 1 a large boost. This means that the lump pass through each other, and basically the theory is transparent. We can recover the lump after the scattering. When j star is equal 1, on the other hand, g approaches a constant which is believed to be 0, which means that the overlap of initial state and final states are small, and this means the theory is opaque. So the lumps that we started with, they just disperse into the background. So our question 1 then boils down to this question: what is the value of j star in 3D Ising? Knowing the answer to that, we would know whether the theory is transparent or opaque at high energy. Okay, to give the answer to that question and to the other questions mentioned before, we use Lorentzian inversion formula as a tool. Lorentzian inversion formula gives the CFT data in terms of the double discontinuity of the correlator. The double discontinuity of a correlator is a simple object built out of the Euclidean correlator minus its analytically continued version. Explicitly, the inversion integral is the integral of the double discontinuity against an S-channel block with funny dependence on J and delta, and a Z and Z bar dependent kernel. Here, this contribution needs to be added to the U-channel contribution to have the full contribution to the inversion formula. Then C contains the CFT data through its poles and residues. So the poles are where physical operators are located, and the residues are the OP coefficient. A couple of comments are in order. The Lorentzian inversion formula is convergent for J bigger than the intercept. The Lorentzian inversion formula manifests the analyticity of the spectrum in a spin by giving an organizing principle for operator of a spin J bigger than J star. And when we are interested in extracting the S-channel data from S-channel data with delta bigger than D over 2, we can then decompose the S-channel and restrict to the first term. However, this decomposition cannot be done when we are close to D over 2.
Can I ask a question?
Yeah.
So you are saying as if the inversion formula has been fully established, convergent, but for example, there are some limits on the convergence in delta, not just in spin. I'm not sure it's known that all the Regge trajectories are analytic and stuff like that. I mean, for example, beyond the leading Regge trajectory, do we really know that all Regge trajectories are analytic and full generality?
Like the
Has it been rigorously shown?
Mm-hmm. So the first arguable formula, as far as I know, has been shown to be analytic for J bigger than the intercept. So yes, it's not shown that for J smaller than
For which delta? My question was for which delta is it convergent? I mean, it's convergent in some strip around imaginary delta, which are far away from the physical values.
Mm-hmm. Okay, so yeah.
Do you have any comment about that? What are the limitations?
Yeah.
Maybe I'm not an expert, so maybe I'm misunderstanding the status, but what is your understanding?
Okay. So I don't know for any delta whether the inversion formula converges or not, but what I would say is that for extracting the subleading twist family, the inversion formula does work for J bigger than J star. But like given a delta belonging not even to a multi-twist family, then then yeah, I don't know. But for the subleading twist family, it works.
Mm-hmm. But when you say it works, for example, has it been rigorously shown that all trajectories are poles, or maybe there can be some cuts? What is known about that?
So yeah. So by construction, yeah, it's not obvious that C includes the cuts, but yeah, okay. Whether the full spectrum can be built from the inversion formula, I don't know the answer to that questions. But for the operators which belong to the double twist family, which are the operators that show up in the OPE, that when I consider the 4-point correlator, then it would give all those operators which show up in the OPE, I would say. But yeah, I agree. In the spectrum, you could have like branch cuts in addition to poles. And yeah, I don't know if the inversion formula is general enough to reconstruct those or not.
Okay, thanks for the discussion.
Can I also ask a question about actually the cool experiment of the bumps bumping off each other? So how precise is it? I think so. The width of these bumps would, I mean, you would have to shift the field insertion a little bit in imaginary time, right? Otherwise, if you just insert an operator, you get an infinite bump. The state is not normalizable to initial state.
Right.
So then if you do this shift and if you keep the normal state finite, it looks like you would never quite be in the Regge limit, because I mean, the operators are always a little bit shifted in the one in the past from the one in the future by say 2 epsilon. So it's not completely clear that you would get the finite limit. And indeed, the intuition would be that if you act with a local operator and you create this bump then starts spreading out at the speed of light. And so the final state is very complicated. Now, it looks like there's some conspiration of limits in which you take the state to be not normalizable in the same limit in which you take the boost to be infinite. And I don't quite understand if that's completely precise or if that's just an analogy. Thanks.
Mm-hmm. So what you're worrying about is the smearing of the lump, causing the Regge limit to not to be an honest limit. Is right. That? I would imagine that you can still smear the lump in a way that you would have an honest Regge limit so that they're actually time-like separated from each other. I don't instantly see the obstruction that you're mentioning, but maybe we can discuss it after the talk.
Sounds good.
Great.
Sorry, I also have a question.
Great.
So you mentioned that you have analyticity up to or above the intercept, but right. As far as I understand, the inversion formula only works for J greater than 1. So what if the intercept is below 1? Do you also have convergence up to the intercept?
Right. So that's the main point of this work. Analyticity, the inversion formula works for J bigger than 1 in every theory. That's because J star is bounded by 1. So that's why we say the inversion formula works for J star bigger than 1, but it's a theory dependent statement. So what we want to study in this work is whether the inversion formula basically works for j big, smaller than 1 or not, whether it can be extended to spin 0 and spin 1 operator, basically. So that's the question that we are trying to answer in this work. So knowing that the intercept is below 1, then it means that the inversion formula is extendable below 1 and can be used. Even though this may not be the case in every theory. For example, in holographic CFTs, I do not expect the same to be true because J star there is a cool one.
I see, thanks.
Okay. Okay. So the final point in this slide is that this decomposition, we don't expect it to hold for delta of order d over 2. So the question is how practically how we extract information from the inversion formula, and the answer is through the generating function. Generating function is given as follows, which is a function which depends on beta, tau, and z. Beta and tau, beta being the conformal spin, is just the sum of the conformal dimension plus conformal dimension plus a spin, and tau being the twist, which is the dimension minus a spin. So here, then the generating function encodes the spectrum through power laws. And we can read off the OP coefficient by looking at the coefficient C and beta. Here, when m is equal to 0, we have the leading Regge trajectory. When m is bigger than 0, we get the subleading Regge trajectory. So that's why I said the subleading Regge trajectory can be read from the inversion formula. This formula can be derived from the formula for the inversion integral. So the generating function is built from the inversion integral. And that's the formula we will use from now for extracting the OP data. So specifically, when we want to extract low twist OP data, when we want to study the leading Regge trajectory, we can then take z goes to 0 limit, and then the sum over the leading, the sum over trajectories, then just singles out the leading Regge trajectory, and it suppresses the subleading trajectories. So taking the same z goes to 0 limit of the generating function, then we get the simplification. We get this simplification. Here, the dependence on tau is canceled, and also the dependence on z is just through the interval of the integral. Here, k beta is just the SL2R block, which is a 2f1 function. And now equating the both hand side of the z goes to 0 limit, then we recover the generating function for the leading trajectories, the families of smallest twist. This is the formula we will use for sigma sigma 0 family for large for beta far from the intercept. To calculate the right-hand side of this equation, we need to calculate the double disk. We don't know the full double disk. So what we do is we decompose the double disk of the correlator in terms of the OP coefficient, in terms of OP decomposition in the cross channel. The double discontinuity of, then the double discontinuity of the correlator is given as a sum over the double discontinuity of blocks. The generating function itself then can be written as the sum of the generating function of where we calculate the generating function for an individual block. Here, C delta prime J prime indicates the generating function for a single block, the contribution of a single block to the generating function. So the only problem remaining is that the conformal blocks in 3D are not known. That's why we use 3D to 2D expansion, and we calculate the contribution of each block to the generating function in 2 dimensions, and then use the 3D to 2D expansion to build the contribution of each block in 3 dimensions. Here, A, M, N are just factors fixed by the Casimir equation. In practice, the error of this method can be reduced to 0 by keeping enough terms in the expansion. However, not that many terms in the expansion are needed to make the error negligible. So that's one of the benefits of this method. Once we have calculated, yeah.
So when you approximated the kernel as G pure, is that throwing away the non-perturbative and 1/spin information?
No, it's just the other one is the other terms. The other term which is the other the other term which has the other dependence on J and delta is just to make sure of the shadow symmetric. So if you want to extract the G pure is enough for extracting delta bigger than d/2. You're not throwing out anything. But once you want to go to delta, for example, smaller than d/2, then you need to keep this term. So that, and also
I see. So it's actually exact for delta greater than d/2 to throw out that. Yeah. Okay, thanks.
I also have a question. What if instead of using this 3D to 2D reduction, you just use some like recursion relations for these conformal blocks in 3D, which generate Z series, but to very high order? Would that be any good?
Yeah, so we did the similar thing for Z bar goes to 1 expansion. This works well for larger span, for when you want to extract information about larger span. However, the expansion in terms of 2D works better when you want to study the low spin. And yeah, so.
But when you say it works better, is there any reason for that? It's just empirically?
Oh, it's because you have you have access to all the range in Z and Z bar. So when you want to go to smallest spin, you wouldn't just need Z bar goes to 1, you need the whole range of Z bar. You have a non-negligible contribution from Z bar finite. And then, yeah, basically 1 minus Z bar finite. So that's why an expansion which is not in terms of Z and Z bar is useful.
But I guess what you have in mind is that there is some formula for the error term of the 2 expansions that you are not showing. That,
yes.
And it's from that formula, it
yes.
follows that this is better than that. But is there such a formula somewhere?
Yeah, so it's, so there's a plot in our paper comparing the two for the stress tensor, for beta equal 5, for comparing the collinear approximation with the 2D to 3D. But but the general statement remains that for when you go to small, so when you're like large beta, the inversion integral is dominated by Z bar goes to 1. Z bar goes to 1.
Mm-hmm.
The smaller you take the beta in the S channel, the more non-perturbative terms in 1 minus Z bar expansion become. The more important the non-perturbative term in 1 minus Z bar expansion become. So to capture those non-perturbative terms, it's good to use something which is basically non-perturbative in Z and Z, which doesn't have an expansion in Z and Z bar. But there is a plot in our paper showing the comparison.
Okay, thanks.
Yeah, and also the error in this method can be reduced to 0 by including enough terms into the expansion. So we will refer to these blocks as exact blocks for our purpose. Okay. Now, once we have the generating function, since the generating function had this power law dependence on power law behavior with tau, then we can extract tau beta by taking Z goes to 0 limit of the generating function. By taking the derivative, that would give you just the exponent. And then the C beta can be derived by just taking the generating function and eliminating the Z dependence. This has been previously used in the 2019 paper by Poland et al. The benefit of this is that no extra fit is needed. You don't have any Z dependent function anymore. However, you have to check that the result you get is a constant as a function of Z in order to be able to trust the result you get. The reason that why it might not be a constant is because of the errors that the procedure introduced. First of all, one error is because we cannot go to arbitrary small z, because we only have access to finite number of terms in the cross-channel sum, and the smaller the z is, the less convergent is the cross-channel OPE sum is. I will show a plot for this explicitly. However, on the other hand, if you choose z to be too large, errors due to the neglected higher twist families in the S channel would dominate. So remember, we had these tau m that we said that they're suppressed. But then if your z is too large, your result would get contaminated by those. So our approach is as follows. Include as many operators as possible in the cross channel. For that, we use the numerical data from the paper by David Simmons-Duffin, 2016. And then we would plot the quantity tau, which would depend on z and beta, which would depend on z. We would fix the dependence on beta, so that it would just depend on z. And then we ask for it to be a constant. And the difference that this tau has from a constant function is a measure of error in our analysis, the error coming from both sources mentioned above. So that's the procedure we're going to take. Okay, so we will see this in action for the stress tensor. So what is 3D Ising CFT? 3D Ising CFT is characterized by having a Z2 symmetry and two relevant operators, sigma and epsilon. Then you also have the multi-twist families made out of these operators. The multi-twist families exchanging sigma, sigma, and epsilon, epsilon OPEs are as follows, where the lowest twist family is sigma, sigma 0. After that, you would have epsilon, epsilon 0. And after that, you would have sigma, sigma 1. Above that, you do not have enough numerical stability to call them operators. However, you could see the hint of higher twist operators. So that plot is from the paper by David Simmons-Duffin, the 2016 paper that I mentioned. Then in the sigma epsilon operator, in the sigma epsilon OP, you would have the sigma epsilon 0 double twist family with good numerical stability. And then you would have the higher twist, however, again, numerical stability. You can't really pin them down. So these are the operator content that we will exchange in our OP, in our cross-channel OP, to calculate the double discontinuity. So the roadmap is as follows. We start by studying the leading double twist family in 3D Ising. This family is, that's sigma, sigma 0 family. We get that family by studying the 4-point correlator, sigma, 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 sigma. We have 3 objectives for studying this family. First, we want to recover the stress tensor as a benchmark case to make sure we know what we're doing. Then we want to obtain the intercept of this trajectory, which is the value of J star for delta equal d/2 to find the answer to the first question. And then we analyze the possibility of analytically continuing this trajectory to include epsilon operator to find the answer to the second question. Okay, so to study the convergent of the OPE cross-channel OPE sum for calculating the double disk, we look at the partial sum contribution of each family. Here, here are the 3 objects we will study. This partial sum includes the first partial sum includes the sum over operators in sigma, sigma 0 family up until J max, where the J max is the x-axis in the plots. And we divided it by, the division by the identity is to get the relative contribution of each operator and for us to be able to compare contribution at different z. So basically the question we want to answer by this study is to find out how small z we can go. Because we know we find out that we cannot go to z smaller than the convergence of our families. So here we see that for z equal 10 to the minus, z equal 10 to minus 4.5 and z equal 10 to the minus 3, the contribution of sigma sigma 0 family is convergent. We see the contribution of sigma sigma 1 family starts to it's for z equal 10 to the minus 4.5, it's not as convergent as sigma sigma 0, but it's still acceptable. However, once we go to epsilon epsilon 0, we see that the convergence is lost and we need higher term in the partial sum to make the family convergent. This is expected because we know that the epsilon epsilon 0 family would contribute as log squared z, and each term just have a log z. So we need infinite number of them to be able to produce this log squared z. So we find that data is not enough to make the contribution of the families convergent for z of order 10 to the minus 4.5 for epsilon epsilon 0 and sigma sigma 1.
I'm sorry, I have a question. Which data here is not enough? What exactly is missing?
So this data, I mean the numerical data from the paper of 2016.
But which particular part of the data did you include from the paper? Because there were like 120 operators. Did you
All
include?
of
them. Okay.
I've included all of them. So the sigma sigma 0 sum that I've shown was the sum of all this family. The sigma sigma 1 was the second one, and the epsilon epsilon 0 was the third one. So all
But
three.
did you include also the other operators which did not belong to any family?
Yes, but those are negligible because they're higher to its contribution. Those don't affect anything. Their contribution is much smaller than the error that we have.
But if those are negligible, then which other contributions could help you if that they're not negligible? Which
So
are
the problem is that those operators are like really high twist, as you can see, right?
Yeah.
The problem here is that we need higher spin in the family. So we need spin more than 40 to make the sum over the family convergent.
But don't you basically know what those guys do from, like, I thought that at large spin, nothing interesting happens.
Okay,
Couldn't you just like pretend that those operators exist there and just add them?
Yeah, that's my next slide, basically, yes.
Ah, okay, okay.
So yes, we know that it's pretty boring at large spin, and we can model the contribution of the large spin operators to the family, and that will give us the way to resum the contribution of the families. As you see, when you have a spin 40, which was what we had with the numerical data, the family really hasn't started converging yet. But once you go to spin 100 and 150, the convergence is pretty well. For sigma sigma 0, we already saw the convergence at spin below 40, so that's fine. So once we include the higher spin guys, we can go to z as small as 10 to the minus 4.5. But then again, if you want to go to smaller z, then higher twist families would become important, and you have obstruction from there. Okay, we also, so we have two ways of getting the tail. One analytically, using the large spin limit of the inversion formula. Another one is using this fit. They are both, they both give the same result within the error bar. Within the accuracy we are interested in. Okay, so once that we have resummed the contribution of the family, we can plot the tau beta for a stress tensor. Instead, we plot the anomalous dimension of the stress tensor. It's basically the same quantity. It's just you just subtract -2 delta sigma from it. the line below the yellow line here is the result you want to get. It's the constant result you want to get. It's not the result of the analysis we have. So how close our result is close, how close our result is to this shape shows how good we are doing in terms of error. This is both in terms of shape and in terms of the distance from this curve. So you see, once you include only epsilon, you're just far from it. As you include more operators, you get closer to the curve. You would also get a curve which looks more like a plateau, more like a constant function. So both the shape and the value is improving once you include more operators. And we see that the best curve we have is from the one with the tail resummed. Yes, that's all I want to say. So this result, the result we get from the tail resummed is both stable in terms of dependence in Z and is close in the value. We expect the stability of the curve to be improved. So this distance that you see, we expect it to be improved once multi-twist families are included in the expansion of the other higher twist, double twist, or other multi-twist families included in the expansion of the double discontinuity.
Can I ask a question here?
Yeah.
So this is basically you have a curve and you're trying to analytically continue that curve to the left onto, in this case, the stress tensor. And this is a fancy way of doing that by modeling the tail and then using the inversion formula. How does the result compare to just taking all the points on the Regge curve and fitting a polynomial or something and then just analytically continuing?
Fitting the Regge curve, sorry, what was the other method you suggested? Can you repeat it?
I mean, if you were to just take all say you pretended you didn't know about the stress tensor,
right,
and took all the other operators in the stress tensor family,
okay,
then you would get some function for the
okay. So you are
dimension as a function of spin.
Tau as a function of beta, basically, or tau as a function of, yeah.
Right. Yeah. What if you just directly analytically continued that? Is that much worse?
Tau as a function of beta, you can, yeah. So what you can do is that, okay, so your question is get tau as a function of beta for higher spin, that everything is easy, and analytically continue it to lower beta to reach
Right.
test.
Right.
Okay, so that would have been possible if we knew the actual form of the Regge trajectory, right? I mean, any fit we involve that it's going to introduce error because we don't actually know. We do have some expectation of what the Regge trajectory would look like, but we don't exactly know what the function is.
Right. You can never really analytically continue from a finite number of points.
A numerical point you have above that as well.
But I guess I'm wondering if including the tail, including this ansatz for the tail, does that amount to sort of assuming a form for Regge for the functional form of the Regge trajectory?
It's quite different, because what I'm doing for the fit for getting the tail is for like very large spin, the contribution of larger spin. I'm not declaring that the form that I'm having for larger spin is extendable to lower spin. It's just gonna work for larger spin, where everything just where everything is just similar to mean field theory. So basically, I'm kind of using the mean field theory result there, but so it wouldn't be the same as what you're suggesting. What you're suggesting, it will be what we're gonna do for the intercept. For getting the intercept, basically analytically continuing the curve, basically for getting the epsilon operator, basically analytically continuing the curve to include the spin that it doesn't. However, you need to make an ansatz for the analytic continuation because every point you have are numerical. So if you can calculate the inversion formula at some point, it's better that you do it.
Okay.
Rather than,
Okay.
yeah.
Thanks.
So these two are not the same thing. Like the analytic continuation, we're not claiming that that are fit for large spin is extendable to low spin. It's for very large spin. It works for spin. Yeah, we use it for spin above 20, right? Or 30.
Okay.
Okay. So the result of the analysis is as follows. If you look at the two best curves that we get, the result we get from the inversion formula gives the twist of the stress tensor with 10 to the minus 4 level accuracy. And the same for the OPE coefficient. For the OPE coefficient, we can again do the same analysis once we extract the tau beta, So now that we have studied the benchmark curves, we are ready to move to the intercept. Two subtleties to mention here. First, that collinear approximation for the S-channel block is not valid when delta is equal to d/2. The second term that I said could be neglected cannot be neglected when we are close to d/2. There's also collinear descendant terms in z goes to 0 limit, which also matters. So instead of dealing with those, we use another expansion of this channel blocks in terms of rho and rho bar, which captures both of the contribution better than z and z bar expansion. Now with this as channel block, the inversion formula must be integrated numerically. We don't have analytic result. Thus, we only include epsilon and t in the expansion of the double discontinuity. So the stability of our result would be moderate from the expectation we get from beta equal 5. It's going to be even beta smaller than 5. So the less stability we expect. So the result for the intercept is plotted here. We compared data from only exchanging epsilon and identity and compare it to epsilon and identity and t. We see that the two curves differ from each other by this amount. We call this the error of our analysis. However, what is clear from our analysis is that the intercept is below 1. This can also be seen by looking at the Regge trajectory where we fully trust it and we have the full match, and then using convexity of the leading Regge trajectory, then we see that it only has one option, which is going below 1. Convexity doesn't allow it to be bigger than 1 using the using the Regge trajectory where we trust it. So this gives the answer to our first question, which is that the 3D Ising CFT is a transparent theory at high energy.
Can I ask a question?
Yeah.
Does this intercept depend on the correlator that you're considering? For example, should you consider epsilon, epsilon, epsilon?
Right.
Would that thing be transparent as well?
Right. So the intercept is what I mean from the intercept is the intercept of the leading Regge trajectory in the family, which is the sigma sigma 0 family. This has the lowest twist. This is the family with lowest twist, and that's what I mean. But if you look at the, for example, sigma epsilon epsilon sigma correlator, you would.
No, I'm interested. What I'm thinking about is like, for example, in QCD, we say, okay, Pomeron has a certain intercept, and that's just the same Pomeron whether you scatter protons or you scatter pions. Okay. As long as that's the leading trajectory with vacuum quantum number. So is the same thing valid for CFTs?
Right. So you want to recover sigma sigma 0, but by studying epsilon 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 correlator. That's your question?
Yeah. So in QCD it would be the same intercept, but what about the CFT?
Yeah, it's the same here. It's you would want to study the intercept of the sigma sigma 0 trajectory. So that's the same that's going to be the same trajectory. The leading trajectory in epsilon, epsilon, epsilon trajectory is also this one. This is the sigma, sigma 0 trajectory.
Yeah, maybe let me add a comment that yeah, there's an expectation that you're going to get the same trajectories no matter which correlator you extract it from. So we assume that, but we've not tested the assumption numerically.
Yeah, this we have not tested it, but yeah.
So I'm sorry, it's something that I should know, but if you look at the data for the epsilon, 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 epsilon correlator, you see there the sigma, sigma trajectory.
Right, but it's something
And-
you can check numerically, right? You can.
And so you see that it's the same trajectory or it's not quite clear?
So
Well, we know for a fact that it's the same trajectory for integer spins, but we haven't
Okay.
tried to extrapolate it away
Okay.
from that.
Because extrapolation involves some other things, and one could imagine that they could. So it's something that needs to be checked. Okay, thanks. I understand.
yeah,
That looks plausible.
yeah, it could be checked with the same procedure mentioned here. You
Okay.
could look at that for epsilon correlator and check that. But yeah, it's expected to be the same. Okay. So once we have the Regge trajectory near the intercept, you can go to answer the second question, which is whether this trajectory can be analytically continued to include epsilon or not. We use a hyperbola as an ansatz for the trajectory. This has the right shadow symmetricness and the right asymptotics in terms of going to 2 delta sigma. Then we fit the data that we get from the inversion formula to this hyperbola. However, we keep the asymptotic and the point of intersection generic. So the result we get is shows us how good we are doing, how good the fit is doing. So even though we know what beta 0 and B needs to be, we keep them general. So the fit would give us A, beta 0, and B. The result of the fit would produce these dashed lines, which you can see is a good fit. It's doing very well for the upper branch. However, for the lower branch, we can see that first of all, the distance from them is not negligible. Also, they do not include epsilon. However, the distance from them is kind of compatible with the distance they have for them to include the epsilon. So our error is compatible with the lower trajectory, including epsilon. As an example, we give the value of the fit of data obtained from epsilon t at z equal 10 to the minus 4. At this value, we get the following numbers for delta epsilon. We see that they're not that close to 1.40, but this is understandable given the instability of the result we have. So partial answer to question 2 is that the analysis is consistent with epsilon being on the analytically continued trajectory. However, the value of delta epsilon cannot be exactly pinned down in a stable way.
Sorry, why was it not possible to use the same method as you used for the stress tensor to do this continuation? It is because it no longer converges?
Mm-hmm. So the main obstruction was the fact that we needed to do the integral numerically because the S channel block here was different from the collinear channel block. For the stress tensor, once we had the collinear channel block, there was analytic results that we used. But here we have to do the inversion integral numerically. For reproducing this plot, I don't know, like thousands of integral has been done. So including more operators would just like was kind of out of hand just numerically,
Okay.
out of reach. So that's the construction. But we know from what we've seen for stress tensor, that the stability is much lower here. And that's expected. So next we study this. Next we study the question of extending the analyticity for the sigma epsilon 0 family. We answered this question by looking at the sigma epsilon sigma correlator. Again, all operators we have are exchanged in the T channel and the U channel correlator to calculate the double discontinuity. First, we wish to study the absence of a spin-1 current in the odd sector. We want to see whether we can show analytically that the that the 3D Ising model does not have a spin-1 operator, a spin-1 conserved current. So we know that if the spin-1 conserved current existed, it would have had beta equal 3, since it saturates unitarily bound. So we probe the vicinity of that value. An interesting thing we observe is that the generating function actually crosses 0 in the vicinity of that value. This is a good sign. However, it's not conclusive, because the operator for which the for which the generating function is vanishing could be any operator, could be an operator not with spin-1 but any other operator. However, we know that there exists an operator for which the OP coefficient is vanishing. Vanishing of the OP coefficient shows that the operator simply doesn't exist in the theory. So in order to reach to a conclusive result, we study a different object, which is J-1 times the generating function. We know that if the operator which is vanishing has a spin 1, then this guy needs to be tangent to the x-axis. Otherwise, otherwise we just cross, If the J equal 1 existed and it had non-zero coefficient, it would just cross the x-axis. So the result that we get is as follows. We see that they are almost tangential. However, they're not quite. There's an error bar explaining why it's not. The error of the truncation can explain why they're not tangential. You can see that the error of truncation matters once you look at the different z's, different value of z. So the error is compatible with the operator with the spin 1 vanishing. However, it doesn't, again, conclusively shows it. One interesting side is that the cancellation in the generating function that we saw earlier is due to the, so we earlier saw that to get the Lorentzian inversion formula, you had to sum the T channel and U channel contribution with a factor of minus 1 to the J. If you're looking at the odd spin trajectory, you would have, of course, minus 1. So it would be CT minus CU. But if you're looking at even spin trajectory, it would be CT plus CU. Sorry. So once we're looking at the odd spin trajectory, we see that there's a cancellation. However, once we look at the even sector, we see that there's no cancellation. This means that the vanishing of the OP coefficient for spin 1 comes from the subtle cancellation between the T contribution and and U contribution. That was just an interesting side. Lastly, we can continue to spin 0. We can, in this trajectory as well, we can push our analysis to spin 0. Here we look at tau beta, similar to what we did for the intercept. We look at it for various value of z to show how stable we are. Again, the stability would be moderate, similar to the intercept. It wouldn't be as good as the intercept, as good as the stress sensor. By crossing the curve tau beta with a j equals 0 line, we find out that all of the curves include a spin 0 operator. However, what we would be interested would be that spin 0 operator being the shadow of sigma, because it's the operator with the right, that we know it exists and it has the right dimension to be. Shadow sigma is this black point, black dot here. We see that, again, it's close to being on the curves we get for tau beta. However, it's not quite, again, on top of it. So similar to what we had for epsilon and similar to what we had for the intercept, we see that the spin 0 of sigma epsilon 0 family is in the vicinity of the shadow of sigma operator, showing that an analysis is compatible with shadow of sigma belonging to sigma epsilon 0 trajectory. However, we cannot fully pin it down. We also look at the OP coefficient of this operator to be able to pin it down. However, we see that there's like a 30% error. So it's still very moderate. So yeah, even though we qualitatively find that there's a spin 0 operator belonging to sigma epsilon 0 trajectory compatible with being shadow of sigma, we cannot numerically pin it down. So the last part of my talk is just summary and outlook. The most stable analysis we did was for the stress sensor, which we drive analytically with the error at the level 10 to the -4. Then we moved to the study of the intercept of the leading rigid trajectory, which we drive to be a further 0.8, showing that the 3D Ising model is transparent at high energy. Then we analytically continued sigma sigma 0, and we looked at sigma epsilon 0 trajectory as well. And we saw that the analytically continued curve are compatible with the trajectories, including the spin 0 operator, respectively, epsilon and sigma. We also saw that the analytic result is compatible with the absence of a spin 1 conserved current in 3D Ising. However, what we saw in the last couple of slides was that controlling error is very hard in this method. We have not succeeded in bounding errors. So it would be good to look for a better approach. So maybe working in terms of inequality and CFT sum rule could be a better approach to attack these questions. Lastly, as an outlook, intercept being less than 1 means that the spectral density of 3D Ising CFT is regular at large dimension. One can explore the application of this for numerical bootstrap and see if it could be used, if it could be of any use. So that's it. Thank you.
Thank you very much. So are there more questions?
I have a question.
Go ahead.
Go ahead.
Can you say a bit more about what exactly it means that the spectrum is regular?
Right. So what it means is that if you look at the double discontinuity of the block, which is just sine squared times the block, the contribution of it to the spectral density, you see that at large delta, it goes as delta to 2 delta to the power 2 minus 2 j star. Right. No, sorry, I think it's the other way around. Yeah, it should be one, yeah, I think it's 2 j star minus 2, so that it goes to 0. So you see that if the operator belongs to the double twist family, the double discontinuity is by itself 0. However, if the operator does not belong to a double twist family, it's like a random operator, then it means that its OP coefficient should be small so that its contribution drops with the power law in terms of large delta.
So you mean that the spectral density is equal to the mean field plus some small correction, which is smaller than what you would have if J star was 1? Is this the intuition?
Yeah. So if J star is bigger than 1, we cannot, or equal 1, we cannot say anything, because you would not have any suppression, because yeah, it's basically it's J star minus 1, delta to J star minus 1. So if J star is equal 1 or bigger, then you wouldn't have any suppression. However, if J star is minus 1, when you look at large delta limit, then the spectral density goes to 0. When I'm saying spectral density, I mean like the special value of it's not actually the spectral density, but it's like 2 sine squared of each operator times the OP coefficient over the contribution. So if, yeah, go ahead.
Yeah, maybe I could say it slightly differently. So the average spectral density is always fixed by the Euclidean OP. You have to reproduce the density in the cross channel. But the thing that's new here is that the average of sine square has to decay at large dimension. So this is telling you that somehow most of the contribution have small and numerous dimensions. So operators with large and numerous dimensions cannot have large coefficients.
Okay, thanks.
Yeah. So the 2 sine squared, yeah, it just goes to 0 when you have a small anomalous, because sine squared goes as anomalous dimension squared.
Okay, thank you.
Is there any way to understand some intuition for why this should be true in the Ising model, or when it's true without doing all these calculations?
So when J star is smaller than 1?
Yeah.
So usually the J star can be thought of as the effective Regge's excitation that is exchanged in the Regge limit. So when you have theories with vector bosons, then you wouldn't expect this transparency, right? So if you have like gauge theory, if you have QCD, if you have holographic CFTs, you wouldn't expect this transparency because you have particles of spin, effective Regge's particles spin 1 and 2. However, for scalar theories, it's kind of expected. What was not obvious in the study of 3D Ising was that 3D Ising does not have a small coupling. So if I had like a scalar theory with small coupling, it was expected. However, what makes it non-trivial here is that we don't have a small coupling. But like, for example, in epsilon expansion, we expect the intercept to be below 1. But 3D Ising is actually like it's epsilon equal 1. So basically it's not a small parameter. So we don't have.
Is there a formula for the intercept and the epsilon expansion?
I think, yeah, that can be calculated easily from the work of all day, like the taming the epsilon expansion paper, I think it was 2017.
Yeah, and we also give formulas for ON at large n.
Yeah,
in
we
the
also,
paper.
it's in our paper, yes. And in enlarge and expansion, you can also see that the intercept is below 1. Up to first order and 1/n.
Is it a good moment to ask again about my confusion on the experiment that I
Right.
was asking at the beginning of the talk? So
Right.
maybe I can ask in a much simplified setup to see where the confusion is exactly. So let's just consider a 2-point function instead of a 4-point function. Let's just try to create some bump and catch it at late times. Right? So we create something, we let it propagate, and we would like to catch it in the future. If this scattering setup should make sense for the 4-point function, then I guess it should in particular give something finite. But it seems, okay, so the confusion arises as follows. As I was saying, so if we normalize the wave packets, so well, it's not a wave packet, but just an operator, so we shift it by epsilon in the imaginary time, then the distance to its homologous in the future, like I'm just really considering the overlap, so it's time order, but it's also like Weidmann. It's going to be something like epsilon times the distance in time. So if you compute the 2-point function, you get something like 1 over epsilon times t to the delta. And once you normalize the two operators, you kill the epsilon, and you're left with something like 1 over t to the delta, which decays when the two operators are very far away. And okay, this I thought had some meaning, because if you let's take for concreteness that this operator we're using is like we're in free theory, and we hit the vacuum with phi squared. So the point is that phi squared creates two particles, which are going to be thrown away in some with some uniform distribution in momentum. And so you're not going to catch the wave packet by just applying phi square in the future, because phi square creates other two particles that come in from the same place, again, with different momenta. Instead, if you try the overlap with phi square with two copies, like phi square phi phi, and you do the same experiment, then you see that you can get overlap 1, because these two particles can be caught far away from each other, which is just like the expansion of this of matter in a CFT, which in free theory is just particles that go in different directions. So since this kind of seems to fail, at least naively, in this way with the 2-point function, then I'm not sure I understand exactly what's the experiment with the 4-point function, and if the Regge limit is really pinning it down.
Okay, maybe I can help answer that. So yeah, the dilution effect is real, and you can detect it in 2-point function, but we're always dividing by this overall dilution when we do our measurement. So when we say that something is transparency, it means that the amplitude will not go to. So there's a theorem that the connected 4-point correlator cannot be in this Regge limit cannot be bigger than this this dilution effect. So we divide by that. So when we say transparency, it will mean that the 4-point function tends to the 2-point function in that limit.
Okay, I see. So there's this 4-point minus disconnected 4-point is also further divide, and this actually works in this part that goes like 1 over t is then cancelled in this case. Because I said 1 over t to the 2 delta, it's cancelled above and below.
Yeah, another thing I would say is that I'm not sure about what coordinates one use, but if you think about having a spatial, a transverse profile that you boost, I think the 2-point function is actually boost invariant. So depending how you parameterize things, this dilution effect may not be.
Well, but I guess that's true if you put epsilon equals 0. No? I mean, if you just have a t plus I epsilon, then I mean that's just the distance is just something like epsilon times t. So it's just like this.
Yeah, that's what. Yeah, exactly. Yeah,
so.
So you make one coordinate large and the other small, such that the product is constant. The rigid limit technically is exactly that. You're taking a large boost.
No, but there's a well, okay, but I think I understand now the fact that this is divided out seems to solve the point. Thanks.
Any further questions? Okay, thank you again, Zahra.
Thank you for listening. Okay, so I should stop sharing.